Hi guys, welcome back to my channel. Today we're going to be having a look at related rates. So this is all to do with derivatives and using differential functions. So let's start off with this problem here. You are inflating a spherical balloon at a rate of 7 centimeters cubed per second. How fast is its radius increasing when the radius is 4 centimeters? Okay, so since this is a rates problem, we want to actually define some of the rates that we have, and we want to define the rate that we need to know. So from what I can see here, we've got this first rate. So if we say that V is equal to our volume, and that's going to be in cubic centimeters, and we say T is equal to time, and that's going to be in seconds, then we can express this as dV dt is equal to 7. So that's the information that we know. The information that we want to know is how fast its radius is increasing when the radius is 4 centimeters. So in other words, so let's write this. So R is equal to our radius, and this is just going to be in centimeters because it's a linear value. And we want to find dr dt. So how do we go from finding dv dt to dr dt? Well, this is where related rates comes in. Effectively, what we want to do is we want to use the chain rule so that we can find this term. dr dt is going to be equal to dv dt times by dr dv. Whew, that was a mouthful, wasn't it? And effectively, what's going to happen is that these changes in volume are going to, I hate saying cancel, but it's a good way of describing what's happening. They're dividing into each other. And then we will be left with dr dt. Okay, so we already have this value here. So how do we now find this value? So this is going to be our related rate that we're going to use. So what we can do, thinking about now going back to this problem, we have a spherical balloon. So if I was going to try to find the volume with respect to the radius, that's going to be 4 pi r cubed over 3. And so when I derive this function, I'm going to get dv dr. And that's going to be equal to, that 3 comes down, so that becomes 4 pi r squared. Okay, so this is not quite in the form that we want it just yet. So what I'm going to do is I'm going to take the inverse of each side so that I have dr over dv is equal to 1 over 4 pi r squared. Okay, so now that I have that information, let's substitute back into that chain rule. So dr dt is going to be equal to dv dt multiplied by dr dv. Sorry, dv dt from before was 7. Dr dv from our inverse function here is 1 over 4 pi r squared. And that is going to simplify to become 7 over 4 pi r squared. The other piece of information that we know, that we are told in the question, is that the radius is 4 centimeters. So we can substitute in our value now for r is equal to 4. So dr dt is equal to 7 over 4 times by pi times by 4 squared. So popping this into my calculator, I get a solution of 0.35, or an exact solution of 7 over 64 pi. So that's how we use related rates. Let's do another quick example here. A square has its sides increasing at a rate of 2 centimeters per second. Calculate the rate at which the area is increasing when the sides are 4 centimeters long. Okay, let's start off with what we have and what we need to know. So we already know that the rate is increasing at 2 centimeters per second. So let's call S our side length, and that's going to be in centimeters. Then we're going to have T equal to time. And we're going to find this with respect to the area. So A is going to represent the area, and that's going to be centimeters squared. Okay, so this rate here, it's 2 centimeters per second. So we can write the change in the side length per change in time will be equal to 2. So the rate of change is equal to 2. We need to find the rate at which the area is increasing. So we need to find dA dt. So we need to find a rate that is going to relate these two terms. And we're going to do that with the chain rule again. So dA dt is going to be equal to dA over ds multiplied by ds over dt. And then what's going to happen is these two ds terms are going to be removed, and we're just going to have this expressed in terms of the area and of time. So how do we do that? How do we relate area and the side length? Well, that's really easy. Again, we're just going to use our formula for the area of a square. We're going to find the derivative of the area with respect to s. And do we need to flip this one like the last one? No, we won't need to flip this one because it's already in that form. So let's put this into our formula. So dA dt is going to be equal to dA ds, which is 2s, multiplied by ds dt, which is 2. So dA dt is going to be equal to 4s. Now the last piece of information that we know is that the sides are 4 centimeters long. So let's substitute this into our equation. So dA dt is going to be equal to 16 centimeters squared per second. So that's how we use related rates and the chain rule in order to solve these kinds of problems where we have areas or volumes or side lengths that are increasing or changing at particular rates, and we're trying to find another rate that is related to that original rate. All right, guys, I hope you enjoyed. See you in the next one.